I'm going to share my screen now. And can everyone see the PowerPoint here? Yes? Could you guys see the PowerPoint?
Yeah.
Yep, okay.
Yeah.
All right, so what we're gonna talk about today is kind of the second half of the data analysis questions. And so we're going to look at standard deviation. We talked about standard deviation a little bit last week, but we're going to do a little bit more with it. Probability, permutation, and combination. So the first one here, this is page 28 in the workbook. So let's start with this. This is a probability question. And so let's see, yeah, number 5 on page 28. And so the way probability works is one way to think of it is you have your number of ways that you can win divided by number of ways that you can play. So a lot of times for probability, a good way to start with your intuition is like gambling, like Las Vegas games, because they have cards or they have dice where like you can predict probabilities for things. So if we were to say like, what's the probability that you have one die and you roll if you have one die that you roll an odd number? Well, let's see, there are 6 faces on a die, right? And then all the odd numbers, we have 1, 3, 5. So 3 out of 6, so the probability is 1/2. So that's kind of the general, like, easiest version of a probability question. Here, number 5, we're gonna look at a slightly more complicated one. So we have 60 jelly beans, 22 white, 18 green, 11 yellow, 5 red, 4 purple. If a jelly bean is to be chosen at random, what's the probability that the jelly bean will be neither red nor purple? So sometimes they'll ask this, instead of saying what's the probability that it is a certain thing, they'll say what's the probability that it's not a certain thing. Does anyone have any idea for, if we're going to do, we've got this fraction here, our numerator is going to be the ways that we win this game. So we win this game by getting a not red or a not purple. Does anyone have an idea for how we figure that out? Carson.
You just like add them together and then subtract from the total.
So 60 minus and then 9, is that right?
Yep. Okay.
Yes, that is definitely correct. There is another way, which is add up all the ones that are not red and not purple, but you're right, this is a faster way to do it. Okay, and then so what do we put in our denominator? Jordan, what would you say we went down here?
$60.
Yeah, right, not super complicated, so we got 51 over 60. And this is in decimal form, so at this point, if you can see a way to simplify this, great. If not, you can just do 51 divided by 60 in your calculator and you'll get it. If you do know that 51 is divisible by 3 and it comes out to 17, you get 17 out of 20. And at that point, you don't necessarily have to, but you can say, okay, well, I multiply times 5, and I get 85 over 100. So it's going to be 0.85. Again, this is a fine opportunity to just put 51 divided by 60 in your calculator and move on. Okay, so everyone good with this? It's the number of ways you can win divided by the number of ways you can play. Sometimes you get it by subtracting. Sometimes you get it by adding up all the different ways. All right, so this is another probability one. This is using a number line. The point of this is to just show you that it's basically the same. You're just getting your information from a different place. So you're still doing the same stuff, but you're extracting your info from a different place. So we've got a number line. From the 5 points A, B, C, D, and E on the number line above, 3 different points are to be randomly selected. What is the probability that the coordinates of the 3 points selected will all be positive? So let's do a simpler version of this question first so we can get an idea of how to do it. What's the probability that if we pick 1 point, just any 1 point, that it's going to be a positive number? because they're telling us that instead of 3 different points are randomly selected, let's just say from the 5 points, 1 is randomly selected. How do we figure out the probability of that?
Take the total number of possibilities minus the possibilities that are negative over the total number of possibilities. So it'd be like 5 minus 2 over 5.
Yeah, I think in this case, just adding up the positive ones is, you know, it's not terribly different here, but I would start from the default of just adding up the ways that you get what you want divided by the total number of ways that you can play. So you can totally do 5 minus the negatives and then, you know, total minus the negatives and get that. I just want you to be mentally prepared for both. So in this case, yeah, we have 3 out of 5. So that's how we would get 1. We have a 3 out of 5. Now there's an important concept in probability, and it's replacement. So you can have with replacement or without replacement. So I want you guys to think, let's say we have a deck of cards. There are 52 cards in a deck. There's 4 of each suit. So you can have like 4 kings, 4 nines, 4 aces, that kind of thing. If we are, I want to show you guys a difference in probability between replacement and non-replacement. So let's say we want to get, what are your odds of getting 2 aces in a row? 2 aces in a row. So we have with replacement and without replacement. Well, with replacement means if you drew that ace, you put it back in the deck for your next draw. So with replacement means you reset the deck every time. So with replacement, well, what are our odds of getting an ace on our draw just for one draw? It'd be 4 because there are 4 aces in a deck divided by 52. So that simplifies down to 1/13. Okay. So we'll say 2 aces and then 2 aces. So with replacement, 2 aces, we get a 1 out of 13 chance to get the first ace times 1 out of 13 to get the second. So it's the first chance times the second chance. It's 1 out of 13, 1 out of 13. So it ends up being 1 out of 169. So that's our chance of drawing 2 aces in a row with replacement. So what about without replacement? Well, the first option is the same because we got a 1 out of 13 chance, or let's say 4 out of 52. 4 out of 52 chance of drawing an ace. But after we've done that, if we're not replacing it, how many aces are left in the deck? Jordan, how many aces are left in the deck?
3.
3. And how many cards total are left in the deck?
51.
51, yeah. So here we're going to get 12 and then 52 times 51. I'm not going to try and do that one in my head. $2,652. And so what we can do is we could check our numbers here, but I think you guys can probably intuitively tell that these are going to be close, but not exactly the same, right? So with replacement and without replacement, which number do you think, or which one do you think has better odds? Let's put it that way.
The first one.
Why
with
do you,
replacement.
the first one with replacement? Why do you say that?
Because there's one more ace to there's one more ace to one more card.
Yeah, their first part, their first fraction, the 1/13 is the same, right? 3 out of 51 is slightly worse odds than 1 out of 13 or 4 out of 52.
Right.
Yeah. Okay. And if you look at the probabilities, they're both pretty low, but the probability for A is just a little bit higher. It's 0.0059 instead of 0.0045. So I don't remember if there's a with or without replacement practice question in this workbook, but there's a real chance that you'll see one or the other, or potentially even both, on the GRE test that you take. So I wanted to cover those, and I want you to kind of understand those for this situation here, because we need to decide when you have multiple events, like what are your odds of doing this then that, what are your odds of doing X then Y then Z. You got to think in terms of, do we have replacement or not, because it changes your odds. So the first probability for 1 point selected will be positive. That's the same whether there's replacement or not. But let's look at this. What's the probability that the coordinates of the 3 points selected will be positive? So once we select this point, we can't, with replacement basically means you reset. You reset the deck, you reset the system. That's not really something we can do here. We have to pick 3 points at once. If we're trying to pick 3 points at once, we're not resetting it. We're taking them all out at once. We can't pick a point and then put it back in and then pick it again. Does that make sense? More or less? Okay. So our probability is now changing. It's not going to be out of 5. We've already drawn 1 point. It's going to be out of 4. And then the third point's going to be out of 3. So what are our odds for the second draw? So we're taking out 3 points at a time. The odds of the first point being positive, 3 out of 5. What about the odds of the second point being positive? Kennedy, what do you think?
2 out of 4.
Yep. And then the last one, there's only one positive left, right? Because we've already chosen one, or already chosen 2 of them. So then it's 1 out of 3. Now, this is not terribly complicated math, but I do want to show you guys, I want you guys to be aware that there can be shortcuts that can work to your favor here for simplifying this. If you see a 3 in any numerator and you're multiplying across, if you see a 3 in any numerator and in the denominator, you can just cancel them out. If there was a 2 up here and a 2 down here, you could do the same. A 5 up here and a 5 down there, you could do the same. So you just want to be aware of that. In this case, it doesn't make a huge difference. But then also we see 2 out of 4. Well, that can simplify down to 1/2. And so now our math's a whole lot easier, right? Our numerator's just 1 times 1 times 1, not so bad. And then 5 times 2, so 1/10. And then depending on what they ask, it's either 1 out of 10 or 10%. Okay. That makes sense to you guys? Everyone feels like they got it? Yeah. It's really important to understand when you use replacement or not, and they'll either tell you with or without replacement, or if you're selecting all of them at once, then there's no replacement. Okay. Now we're going to talk about standard deviation and normal distribution. Go ahead and just draw your version of this on your notes. It's not a big deal. It doesn't need to be perfect. And I am going to share this with you guys later, but I want you guys to kind of fill it out as we go, just to make sure everyone gets what we're talking about. Have any of you dealt with a normal distribution before? Carson, you have? If you just wanted to kind of describe a little bit about what a normal distribution is, what would you say?
It's been a really long time, so this might be wrong.
Okay.
But basically, the distribution of values adheres to the curve, so where you know that, I don't know, I remember there's certain numbers that basically go certain places, and you can make assumptions about the data based on where in the curve it is because everything's evenly distributed.
Yeah.
I don't know if that's the right word, but there's norms to it.
Yeah, okay. That's not incorrect. I'm going to just briefly talk about some stuff that's not in the GRE to just give you a sense of what normal distribution is, and then we'll quickly go into what the stuff you need for the GRE. So if we're just collecting values of anything, they can follow typically a power law or a normal distribution. The power law thing you guys don't need to care about. And the power law doesn't look like this, it looks like this, which basically means if we go by, if we just surveyed all the stars in the universe and we're looking at them, most of them are going to be very small. A small fraction of them are going to be massive. So it's not like most of them are medium sized and then there's a few that are big and a few that are small. No, most of them are pretty small and very few of them are massive. And so it doesn't have the hump here of the normal distribution. But other things have the normal distribution, and those are things where most things are clumped in the middle. So if we go by height, most people are around average height. A lot of people are average height. And then if you go out to like who's within an inch or two of average height, a lot of people are within that. And then as you go farther and farther out, the more extreme people's heights are, the more unusual it is. And so that's a normal distribution. A normal distribution, like Carson said, there's a lot of stuff that you can predict about it based on that. And so anything that has a normal distribution, you can infer a lot of things about it. A lot of things with about people, about animals, follow a normal distribution. So you can have height, you can have weight. I'm trying to think of some other things. A lot of times, like scores on a test follow a normal distribution. So if we were looking at GRE percentiles, those follow a normal distribution. And so that's what we're going to focus on for the GRE. So normal distribution, and the way they break this up, this has to do with standard deviation. So you have your mean in the middle. So your mean is your average value. And then one way to communicate like how unusual or how far from the mean we are is to break it up into standard deviations. So if we add one standard deviation, this would be 2 standard deviations. And this would be minus 1 standard deviation. And this would be minus 2 standard deviations. Now these aren't randomly chosen, and we'll talk about what they mean. But basically the way they're chosen is you want about 34% of your total values to be between the average and plus 1 standard deviation. And then a negative standard deviation below the mean, you want about 34% of your values to be there. Then you want another 14% of your values to be between 1 standard deviation below and 2 standard deviations below. And then you also want 14% of your values to be between 1 standard deviation and 2 standard deviations above the mean. And then you have your other 2% here. Now these are slightly rounded numbers, but as far as you need to know for the GRE, this is it. And you typically don't even necessarily have to have these numbers memorized, but it is important to understand, like, if you look here, 68% of the values are within 1 standard deviation plus or minus. That is an important thing to understand. More than half of the values are within 1 standard deviation plus or minus. So if we were to take, let's say, I think the average height for a woman in the United States is 5'5". So let's do this. So 5'5" is our mean. And I'm pretty sure this isn't true, but let's just say 1 inch is a standard deviation. So 1 inch equals 1 standard deviation, which means 5'6" is 1 standard deviation above the mean, 5'7", 1 standard deviation, 2 standard deviations above the mean, which also means 5'4" is 1 standard deviation below the mean, and 5'3" is 2 standard deviations below the mean. So with these percents broken down, we can kind of say a lot of things about where people are on this. And so one way to think about it is, let's take someone who's 5'6". They're 1 standard deviation above the mean. That also means that all the numbers here add up to the values that they're taller than, and all the numbers on this side add up to all the numbers that they're shorter than. So they are shorter than 16% of other American women, and they're taller than 84%. Now, what I could have done here is said, okay, 34 plus 34 is 68. 68 plus 14 is 82, and then 82 plus 2 is 84. I could do that, or I could say the whole thing adds up to 100. Let's just subtract 16. So someone who's 5'6" is in the 84th percentile in height. You can say they're taller than 84% of American women. You can say they're shorter than 16% of American women. Does this make sense to everyone so far? Okay. What about someone who is 5'3"? I would like for you guys to figure out what percent taller they are than other American women and what percent of American women they're shorter than. So go ahead and figure that out, and then I'll ask you guys. So we have a woman who's 5'3". She is taller than what percent of American women and shorter than what percent of American women? Okay. Carson, let's, what did you get here?
So you would be at that like second standard deviation point, right?
Yeah, two
Yep.
standard deviations below the mean.
Right. So you would be taller than 2%
Uh-huh.
and shorter than 98%.
Yeah. And another way to put it is you're in the second percentile in height. Now, I'm pretty certain this is not correct, that 1 inch is not a standard deviation. It's probably something like 1.5 inches. But this is just to help you guys get the picture. So another thing that you can do is estimate pretty well where someone is. Let's say that we have a woman who's 5'6.5", okay? So that's around here. So if we were to break that up perfectly, we could say, oh, well, 2% plus half of 14 is 9%, right? And so then we have 91%. So they're in the 91st percentile. That's not a terrible estimate, but if you notice here, there's a lot more space in this half than there is in this half. There's a lot more space in the blue half than there is in the green half. So if I were to do that, I would say something like, I don't know. I'm gonna take some more out of this. I'm gonna say this is like 94th percentile, and I'm gonna say this is like the 6th percentile. Now, if they're trying to get you to estimate on a normal distribution, it's also called the bell curve. If they're trying to do that, this is as hard as they'll go. So I just want you guys to see like a full understanding of this. One thing that might come up, but it might not, is a z-score. A z-score is a standard deviation. So a z-score of 2 means plus 2 standard deviation. A z-score of -1 means 1 standard deviation below the mean. So what's nice about the normal distribution and standard deviation is if I give you two numbers, if I just say the mean is this and the standard deviation is that, you can make a lot of predictions that are going to be fairly accurate about values of the set of numbers that you have. Does that make sense? Okay. So let's take a look. Let's do this here. So we'll take a look at no, that's not what I wanted. We'll take a look at a standard deviation question here. So this is on page 112 in your workbook. And I think what I'm going to do is maybe just set you guys up and let you guys try it. Number 12, for a certain distribution, the measurement 12.1 is 1.5 standard deviations below the mean, and the measurement 17.5 is 3 standard deviations above the mean. What is the mean of the distribution? So my first hint here is going to be, let's just draw, let's do this. Let's see if I can copy this and shrink it. And so I'd like you guys to just make a real quick drawing like this and use that and see if you guys can estimate the answer. I don't want you to actually get the answer, but if you feel confident that you can get the answer, go for it. But if not, just try and estimate your answer. So I'll give you guys a minute to try that. Okay. Carson, why don't you tell me what you did for this one?
So I just like estimated and actually got it wrong.
Okay.
I assumed I was close. I put 13.8.
Mm-hmm.
And the reason why I estimated it that way was just that if 12.1 is only 1.5 standard deviations below the mean,
Mm-hmm.
and 17.5 is 3 above, then obviously like 17.5 is going to be like less than 2%. Isn't it like, it's like 0.5 or something, right? It's like really tiny.
Yeah. It's actually, I think it's like 0.002, 3 standard deviations. We can look that up. It's unlikely you need to know, but one way to put it, if we go back to our standard deviation here, we've got 2% here, right? It's like 0.02 for the third, to get to the third standard deviation, there's 0.02 left here. So it's pretty small. But it's okay. It's sometimes you'll get answer choices that are really close together like this, and then you really want to be precise. But I want you guys to like get some practice using your intuition on this. So it's okay if you miss it, but I want you to like build on that intuition a little bit. So you're saying 3 standard deviations is definitely farther away than 1.5 standard deviations, right?
Right. So I guess that would be like so significantly far away that it would be like one of the numbers that's closest to 12.1. I guess like you would solve it algebraically if you fully solved it out. You can do that, right? Like with
Yeah. Yep. So let's just kind of eyeball this to get a sense of what's going on. So 12.1 is 1.5 standard deviation. So this, let's say this is the mean and we don't know what it is yet, but 1.5 standard deviations is right here. So we'll say that's 12.1. And then 17.5, well, this is 1, 2, 3 standard deviations. So this is 17.5. So if we're just eyeballing this and we don't even look at these numbers, I think it's pretty clear that something around 14 makes sense, right? Because if we wanted, like, let's say we're just trying to estimate the midpoint between these two. Well, the midpoint between 12.1 and 17.5 is about 15-ish, right? So that's going to be somewhere like here. So we're definitely going to be below 15. It's going to be something like 14. Okay. So that if our numbers are all over the place, then we can kind of eyeball that. But let's figure out exactly what's going on. Well, one way to look at this is the average. So we'll just call it M for mean. So the mean minus 1.5 standard deviations, and we'll just call it 1.5s equals 12.1. Does everyone get what I'm setting up here? And then we have the mean plus 3.0 standard deviations is equal to 17.5. So does anyone have an idea of what we can do now? How we can deal with these? We're trying to get the mean, right? So we're trying to figure out a way to get rid of standard deviations when we combine them. Because if we add them right now, we get positive 1.5 standard deviations. 2 times the mean equals, so I'll just add this just to show you guys what happens. We get 29.6, and then negative 1.5 plus 3, we get 1.5 standard deviations, and then 2m. So that's not going to do it for us. Okay, so what else can we do? I want to make the standard deviations go away. That way I can just deal with the mean, because that's what I'm trying to get. So at this point I would say, you know what if I just double all this? If I double this, then I now have 2m minus 3.0 standard deviations equals 24.2. And then if I add these, now I can do something, because negative 3 standard deviations plus 3, that's going to give us 0. And then 2m plus m, that's going to give us 3. And then 24.2 plus 17.5 gives us 41.7. And at that point, we can divide everything by 3. And then we'll get 13.9. And there's another way to do it too that I'll show you guys in a second, but I want to make sure everyone understands what we did here, because this was a little bit of a systems of equations question. So just to recap it, we said, okay, the mean minus 1.5s, 1.5 standard deviations is 12.1. The mean plus 3 standard deviations is 17.5. They told us those things. So I'll underline this and this. So we turned those into equations, and then we realized, hey, we can cancel out the standard deviations if we double the first equation, and then we can add them. And so we did that, canceled it out, solve for m, 13.9. Another way we can look at this is say, well, this is negative 1.5 standard deviations, and 17.5 is plus 3 standard deviations. This is basically, if we were to split this up, this is like 2/3 of the way, 2/3 of this. So another way to put it is our total here is 4.5. The distance between them is 4.5, right? Well, 1.5 over 4.5, that gives us 3. And 1.5 over 3 is 2. So we actually have a ratio here of 2 to 3. Actually, I wrote that wrong. Yeah, there we go. So our ratio is 2 to 3. Basically, if we do that, we realize our distance is 4.5. We're going to multiply that. We're going to say, well, so this is a distance of 1.5. And this is a distance of 1.5 plus 1.5. So if we break this up, yeah, actually, I think let's just drop these here. I think it'll be easier to kind of graph this here. So the distance here, this is 1.5 standard deviations. The distance from here to here is 1.5 plus 1.5 standard deviations. Can you guys see that 1/3 of it, this is 1/3 of the distance up here. And then this is 2/3 of the distance up here. Does everyone kind of see that? So we have a fraction that we can use. If we're trying to get from 12.1 to the mean, we could say, all right, 12.1 plus, and it's 1/3 of 4.5. 1/3 of the total distance between them to get to here. And so that would get us to 13.9. Another way to think of it is let's go with 17.5 and work our way back. We're going to subtract 2/3 of the total distance, right? 2/3 of the total distance, which is 4.5. The total distance is 4.5, and that'll get us 13.9. So I just wanted to show you guys kind of a couple different ways to get this. One is to just set it up algebraically, to take these two equations that they gave you in words, translate them to math, add them up so they can cancel out. This sort of dealing with systems of equations is called elimination. And if you're unfamiliar with that, that's something you can look up in Khan Academy. And then here it's just realizing we've got a ratio here. That if we split it up into increments of 1.5, then we have one increment of 1.5 here, 2 of them here. So 1/3 of the distance is in here, 2/3 of the distance is here. And we can multiply the total distance by the fraction here to figure out how far to go to the mean. Okay, let's take a break here. So we'll do a 5-minute break and then we'll come back and we're going to talk about permutations and combinations. Okay, let's start back up. So now we're going to talk about permutation versus combination. And so there aren't a lot of these questions on the GRE, but they always have a couple. And the first thing you want to do is be able to sort between the two. So permutation, break it up this way. For permutation, order matters. So let's say that we have a set of, well, we'll talk about prizes here. Yeah, let's talk about prizes. Let's say there's a drawing and you get something for first prize. Usually what they do is the biggest prize you get for first prize. Then they give you something for second prize that's not as good, but still nice. And then something for third prize, which is usually not super impressive, but I guess it's better than nothing. So we could say first prize, second prize, third prize. So for combination, the order doesn't matter. and everyone gets the same prize. So it could be like a trip to Hawaii. It doesn't matter whether you won the trip to Hawaii on the first round or the second round or a third round. It's the same trip to Hawaii. So we want to know the difference between those. In permutation, the order matters. In combination, it doesn't. There are some key phrases or wordings that can help you sort between the two. And so for permutation, arrangement, or how things are arranged, or certain things can be arranged, that's a key word for permutation. Because if you think about it, for arrangement, it's not just what is in the group, it's how the group is arranged. So that's a permutation. And for combination, you would say selection. Words like selection, select, chosen, that's implying that you're picking a group, but that the order doesn't matter. So if they say, oh, you were selected to go on a trip to Hawaii, they're saying like you were one of those selected. So there's some math stuff that you guys may have seen for permutation and NCR for combination. We're not going to spend too much time on that. If you want to learn more about it, then we could do that. You can do that in Khan Academy. But I kind of, what I want you guys to get here is more of the intuition, because you can learn the formula and apply it. That's not that big a deal. We're going to talk about the formula a little bit, but I want to make sure that you guys kind of get it, because they'll give you plenty of questions where you could use the formula, but it's a little bit clumsy, and just thinking your way through it can be more effective. Okay, so again, permutation order matters, combination it doesn't. So there's a consequence of this. For permutation, one way to think about it is if we have ABC, CBA, or let's simplify it down. Let's just do 2. If we're arranging A and B, we can have AB and BA. That's 2 different arrangements of B and A. So there are 2 permutations here. But if we're doing combinations, AB and BA are the same set. So it doesn't matter whether we pick A first or B first, we're picking them both. And so again, the order doesn't matter. We're just doing A, B, and BA are the same combination. So a different order is a different permutation, whereas a different order is the same combination. So let's do kind of an example that we can compare the two. So let's say we have 5 people. And we are going to choose 3 people from that group of 5. But we're going to choose them, let's say that we're going to make one the president, one the vice president, and one the secretary. Let's say it's of a club. So we're going to randomly select 3 people. One's going to be the president, one's going to be the vice president, and one's going to be the secretary. Do you guys think that's a permutation or a combination? So we're going to choose 3 from 5.
Permutation?
Yeah, because the order matters, right? The president's not the same as the secretary. So the way we're going to do this, I'm going to show you guys kind of the long way, and then I'll show you how it ties into the formula here. If we have 5 people, the possibilities are 5 factorial. So we can do 5 times 4 times 3 times 2 times 1. However, it's not quite 5 factorial since we're choosing 3. So one way to think of it is if we were choosing groups of 5 people, it'd be 5 factorial. So we're choosing 3 from that. And the way to think about it is you want to divide it by 5 minus 3, so 2 factorial, 2 times 1. And if you see that setup, that's how we do permutations. So what you do is you think like if you're choosing 3, we call that R. So R equals 3. And if we're from a group of 5, then N equals 5. And so the way this formula works for permutation is N factorial divided by N minus R factorial.
So just to get this straight, let's say it said instead of choose 3, choose 4. Would it be 3
Divided
times
by
3?
1 factorial, but 1 factorial is just 1. So if it said choose 4, you still have 5 factorial as your numerator, but you're going to have 5 minus 4 as your denominator, which would be 1 factorial. Does that make sense? Okay. And we can,
Yes.
go ahead. And so hopefully I'm going to show you guys a way to simplify this that will hopefully shed some light on why we do it that way. Okay, if I cancel these out, if we look here, there are 3 numbers here, right? That's where the choose 3 comes in. We have 5 times 4 times 3 possibilities. Do you guys see how that's connected? So I'll show you guys another way to look at this for permutation. Okay, we have 5 people and we can choose 3. How many ways are there to choose? And this ties back to our playing card example for probability. How many ways are there to choose 5 people, or sorry, to choose 1 person from 5 here? There are 5 possibilities, right? Because we can choose any of the 5 people to start with. Well, to choose the second person, we now only have 4 possibilities, right? Because one of those people's already chosen. All right. To choose the third person, we only have 3 possibilities. Because 2 of them are already chosen, we have 3 left. And so that's why it's 5 times 4 times 3. And so with permutation, you can think of it as 5 people choose 3. Oh, well, I'm doing 5 factorial, but I'm doing it 3 levels down. I'm doing 5 times 4 times 3 and stopping after 3 because I'm only choosing 3. With combination, this sort of intuition is a little bit harder. And so that's why sometimes it's easier to just kind of remember this rule and then the combination rule that I show you guys. But for permutation, this is fine. Okay, so let's talk about combination. Again, the order doesn't matter. And so with our choices here, we're going to have fewer possibilities here. 5 times 4, so this is 60. Just so we know we have 60 possibilities. So we're going to have less than 60 for combinations. Because let's say that our winners are Kennedy, Carson, and Jordan. Here, it matters who gets picked first. Here, it doesn't matter who gets picked first. So there are fewer unique setups. The number of setups that's unique is less. So we still have 5 factorial number of ways to set this up. And we're still going to divide by n minus r. So we're still going to divide by 2 factorial. But we have to account for something here. Each of these groups of 3, with the same 3 people in it, the order doesn't matter, and so they're all the same. So if we think of our group of 3 as, let's just say, Kennedy, Carson, Jordan, we can do Carson, Kennedy, Jordan, and we can do this, and there are 6 possibilities there. The way that you factor this into a combination is you do 5 factorial divided by 2 factorial. R, the group that you're choosing, goes in your denominator as well. So for combination, it's 5 factorial divided by 2 factorial times 3 factorial. It's almost the same formula as permutation, except whereas this is 5 minus 3, you're doing 5 minus 3, but also the 3 itself as your factorial in the denominator. So if we simplify this, we have 5 factorial over 2 factorial. We know that's already 60, right? Because we did it here. So we have 60 over 3 times 2 times 1. And 3 times 2 times 1 is 6, so we have 60 over 6, and that gives us 10 possibilities. So if we notice that, that's a lot less, right? And if you look up here, if we had done all of our possibilities with the 3 different, or with the combinations of Carson, Kennedy, and Jordan in different orders, there's 6 possibilities there. That's where this comes from, and that's why you divide by 6. Because you want to say like each of these different groupings is the same. It's not unique. So I'll just put dot, 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 because I don't want to draw it all out, but that's 6 possibilities there. Does anyone have any questions on this? This can be a little bit complicated. Obviously, you can come back and look at the video. But everyone kind of get the gist of what's going on. You don't need to have all of this memorized. What I definitely need to make sure that you guys understand is permutation, order matters. Combination, the order doesn't matter. The keyword for permutation is an arrangement. The keyword for combination is a selection. And then how you can set up the factorials for these. There is that shortcut up here for permutation, but that's something that you might not want to mess with if you feel like, oh, I just got to, I need one thing that's going to work all the time. It's the n factorial over n minus r factorial, or in this case, you have n factorial over n minus r factorial times r factorial. So if you memorize these two and this is just the slight difference, then you're fine. If you ever forget which formula should go where, if you notice this one's going to make your number smaller, right? The combination one, because you have something else. You have the r factorial, you have that extra in the denominator. That's going to make your number smaller. And that makes sense because your combination number, there are fewer unique combinations than there are permutations. Okay. So let's take a look at, does anyone have any questions before we move on from this? Jordan, you look like you're thinking about whether you want to ask something.
No, I'm good.
Okay,
Thank you.
No problem. All right, so let's look at this one here. This is on page 175 in your workbook. Okay, so we've got a set of numbers. And quantity A is the number of 4-member subsets of S. And quantity B is the number of 5-member subsets of S. Now, when they say number of sets, they're talking about either a permutation or a combination. The broad term for both of these is called combinatorics. Yeah. So it's either permutation or combination. Does anyone have an idea of which one we're talking about?
The combination.
Yes, you're right. How come?
It doesn't give any indication about order. It just has subsets of people.
Yeah, right. It's a selection. It's not an arrangement. And you're right. It's it doesn't tell us about order mattering. Okay. So you're right there. I would like you guys to try and apply, and just to take a quick look here. Here's our combination one, right? I want you guys to try and apply the combination and figure out what the answer is. And so actually before that, let's before you guys calculate the actual combinations of each, I want you to just think and tell me like which one you think is the right answer. Quantity A, quantity B, they're equal or we can't tell. So it's the number of 4 member subsets of S. So how many groupings of 4 can we do? And how many groupings of 5 can we do? What do you guys think there are more of? Are there more groups of 4 or more groups of 5 in this one?
4.
How come?
Because you're asking for a combination of 4 numbers, and you can have more combinations of less numbers than a combination of more numbers. I know that's jumbled, but it's harder to have an increase in number in a 5 combinations than 4.
Yeah, what you're saying is true. So let's try and exaggerate this because they obviously pick 4 and 5 because they're close together, right? What is the number of 8-member subsets of S? Because S has 8 numbers in it, right? What are the number of combinations for a group of 8 from this set of 8? There's just one, right? There's only one way. Since the order doesn't matter, there's exactly one combination of 8 numbers from this set of 8 numbers, right? So you can't go less than that. If there's only one way, one combination, then that's the smallest you get. So with the bigger the group, right, the fewer combinations you have. And so, yeah. Okay.
Did they make it that easy on purpose?
What do you mean?
Like that's not even one that you would have to really do math with, right?
If you're comfortable with the concepts tested, almost all of these you don't actually have to do a lot of math. They call it quantitative reasoning because of that. And so what I try to do and what Vince tries to do too when he's teaching his math classes is we try to show you that there's more than one way to solve these and you can actually reason your way through a lot of them, but you have to be pretty comfortable with the concepts to do it. And so you just reason through it and you're like, oh my gosh, this is an easy question, right? A lot of them are this easy when you know what's going on. But you guys are taking the GRE because you want to do something important in grad school, not because you're trying to become GRE experts. So you don't have to get to the point where you can see like a quick, short, easy way for every question. You just want to have something that works for all of them, and you want some fraction of them you can see through them and do them quickly. So I'm glad that you saw through it that way. They're all like this. It's just that some of them you know the background math better, and so you can do something like this a little more easily. Does that make sense?
Absolutely.
Okay. So now let's prove it, right? In one way, like there's the kind of like standardized test logic that you just applied to figure this out. And now we're going to do kind of the textbook math way to prove this, right? So with the combination formula, I'll just write that here. You guys were right. It's a combination. So we're going to do n factorial over n minus r factorial times r factorial. And R is the size of the group and N is the size of the set, right? So we've got 8 factorial over, and then for this one, we've got 4 factorial times 4 factorial, right? And we can multiply all this out if we want to, but that's kind of a pain. So what we'll do is we'll say, 8 factorial is 8 times 7 times 6 times 5 times, and then instead of doing 4 times 3 times 2 times 1, let's just say times 4 factorial. So we're kind of expanding this, but not all the way, because 4 factorial and 4 factorial, now we can just do this. And if we do that, okay, well now we just have to worry about, we've got 8 times 7 times 6 times 5 over 4 times 3 times 2 times 1. Before we multiply all this out, what I want is to see like maybe there's some stuff we can simplify here, right? So if I look here, I can say, well, 8 over 4 is really just 2 over 1. Okay, that helps. 6, let's just divide 6 over 3. We'll make that 2 over 1. And so now I'm doing 2 times 7 times 5 times 2. I want to make my math easy. So let's just do 5 times 2 because that's 10. 10 is an easy one. 2 times 7 is 14. 14 times 10 is 140. Anytime you have to multiply, if you can make a 10 out of something like a 2 times 5, always do that because multiplying by 10 is super easy. You just tack on a 0. So we've got 140 up top, and then we've just got 1 times 2 times 1 times 1. And so that cleans up to 70. And I'll try and keep this over here because we have quantity A is 70. I would like for you guys to do the same. So set up your factorials, simplify them as much as you can, like look for things where you can simplify parts of them so that you're not multiplying as much. And I'd like you guys to do the same and find out what quantity B is, what the actual number for quantity B is. So I'll give you guys a couple minutes to do that. And just in the interest of time, I'm going to write it out on up here, but I want you guys to not look if you're trying to solve it. Okay, did anyone not get 56? Jordan, were you still working?
I just got that.
Okay, everyone got 56? Thumbs up? Okay, all right, awesome. So this is a slightly more difficult one. This is page 203. We've got 5 letters in a list. So letters, license plates, this is kind of a classic thing for them to do. 5 letters in the list, G, H, I, J, K, are to be rearranged so that G is the 3rd letter in the list and H is not next to G. How many such arrangements are there? Rearrangements. So this is a permutation. How do I know that? Well, they just said arrangements. The order does matter also. That's another way. So this is a permutation. Now, just to kind of go through this logically, if we look here for this, we did 5 choose 3, so we did 5 times 4 times 3, right? Let's look at this one here. So what do we have? We have 5. And as far as what we choose, we are choosing all 5. So like the simplified version of this, the like level 1 version of this would be, how do we rearrange the list? Well, for the beginning, let's say we don't have to worry about G being the 3rd letter and H is not next to G. Let's say we don't have to worry about that. Then what we would do is say we got 5 of them, we're choosing 5, we just do 5 times 4 times 3 times 2 times 1. We're just doing 5 factorial. We're doing this, right? That's the simplified version of it. But we have some problems here. I wouldn't say problems, we have some complications. G is the 3rd letter. What that means is that if we were to kind of put these in a box here, we have 1, 2, 3, 4, 5. We have 5 places to put all of our values. That would be if there weren't any constraints, but there are. Okay. One of those constraints is that G is the third letter. So this one here is G. That limits us a little bit. What that means is that we think we have 5 that we're choosing from, but we really don't. We really have 4 because G isn't part of that set. They kind of gave us G as if it was something, but it's not. It's set there. So what I'm going to put is a 1 here in spot 3 because there's only one possibility that we can do. There's only one possibility. And since we're only choosing 4, then how many possibilities do we have for this first slot? Carson, how many possibilities do we have for this first spot here?
4, right?
4, yeah, because we can't choose G. So we can choose any of the others, okay? So, all right, how many possibilities do we have for this second slot? Now, we have to remember H is not next to G. So we can't have H, and we can't have G. So we'll put H crossed out and G crossed out. We can't have H and G here. And we already used this one. We already used one spot here. We already used one of our letters. So how many options do we have left? Jordan, what do you think?
Just I and J. So 2.
Yeah. Mm-hmm. So at this point, we've used up 3 of our options, 3 of the 5, right? But we still can't put H here.
So then would it just be 1, 1?
Let's see. So there's a step here that we kind of need to like branch off. Yeah, let's do it this way. So that's right. So one of our possibilities, so one of our situations, we have 8 possibilities here. And I think the easiest way to do this would be to actually let's do this. So we've got, I think an easier way to explain this is we'll do G in the middle. And we're going to do the 2 possibilities with H. H is not next to G. So let's do H here and let's do H here. Okay, and so that's going to be 1 times 1 and 1 times 1 for these. Okay. So I think this will be an easier way to show you guys how to do it. So these are our 2 possibilities. They said H can't be next to G. Or sorry, I'm going to put not H here, I should say. So what are our possibilities here? Let's start with this one where we have G here and we have not H as our option here. how many possibilities do we have in this first one? We have 4. And so now we're down to sorry, what I'm going to do, instead of doing the not G's, I think it'll be easier here. We're going to put the possible places where G is, or sorry, where H is. Yeah, okay. So we've got G is in our third spot here. And where are all the places where H can go? If H is not next to G, let's do this. So if H is not next to G, where can H go? H can go here, right? H can go here. And that's it, right? So you guys are cool with this part so far? So we have G has to be in the third spot and H can't be next to G, so it can either be in the first spot or the fifth spot. So how many possible numbers can we put here? Or letters, I should say. 3, yeah. And then if we use that up, then we're down to 2 possibilities here and 1 possibility here. So we have 3 times 2 times 1. So that gives us 6 possibilities if H is first. Okay, now we're going to do the same thing here. How many possibilities can go in here? Well, we have G and H already set, so we have 3. And then we can do 2 spots here. And then we can do 1 spot here. And so then we get another 6 if H is fifth. So we end up with six options where G is in the middle and H is first, and 6 options where G is in the middle and H is last. And what I want you guys to take away from this is you kind of start from this factorial here for the permutation. And what you want to do is you want to think like, how do I accommodate the constraints that they put on me? So in this case, G is the third letter. Okay, I'm going to put G in the third spot, and that removes how many possibilities I have to start with. H is not next to G. Well, one way to do that is to put where H isn't and to use that to limit them. But I think in this case, it's probably easier to say, well, if H is not next to G, where can H be? And then you're filling those in. So it's almost like if you have you're starting from 5 times 4 times 3 times 2 times 1. You lower the number of possibilities when a certain block is frozen. So we're freezing this one, we're freezing the third block so that there's only 1 possibility there. And then sometimes we're freezing the first block and sometimes we're freezing the fifth block. And so then that limits our possibilities. So you think of it as the complete unhindered number is 5 times 4, 3, 2, 1. So 5 factorial. And then anytime they give you a constraint, if they set a certain choice in that spot's now frozen down to 1, and then it limits the rest of what you can do. Okay. So that's it for today.
Thank you.
Let's see. Yeah, I think, yeah, okay. I might send you guys a homework one. There's some good like license plate questions for this where you have, a license plate has 7 digits, but some parts of it can be letters and some parts of it can be numbers, and then you kind of have to deal with it that way. So I might give you guys another video, kind of like I did for last time, and see if we can do that. So that'll be it. Okay. I'll check in with you guys on Friday. I'll check your progress on your studies, and let me know if you have any questions. And then next week we're going to be doing geometry. All right. All right, guys.
Thank you.
Have a good night.
Thank you.